Let's go ahead and find all of the things for this rational function here. So we want to find the vertical and horizontal asymptotes. Vertical asymptotes, remember, are where we divide by 0. Horizontal asymptotes happen as end behavior. So I remember horizontal as to infinity, and vertical is we cannot divide by 0. So to figure out where we're potentially dividing by 0, let's go ahead and factor the denominator. What multiplies to give us negative 20 adds to give us 1. That would be 5 and negative 4. And let's go ahead and factor the numerator right away as well. We got x minus 2, x plus 1. From here, we can clearly see that if I were to plug in negative 5 or 4, we would be dividing by 0. And I specifically know that those are vertical asymptotes. They're infinite discontinuity because we can't cancel those quantities with anything in the numerator, right? If we could, then we'd have removable. So we got vertical asymptotes at x equals 5 and at x equals, x equals negative 5 and x equals 4. I want to write these as lines because that's what vertical asymptotes are. Whoa. Horizontal asymptotes happen when we're looking at end behavior. To look at our end behavior, we're only going to focus on our leading terms, right? Everything else gets left behind as we're going to infinity, right? What grows the fastest is the leading term. So we end up with x squared over x squared, which just equals 1. So our horizontal asymptote is y equals 1, remembering that horizontal lines are y equals, vertical lines are x equals. Up next, intercepts. To find the x-intercepts, well, what we need to do is we need to set our function equal to 0. The only way to get a fraction equal to 0 is to have 0 in the numerator. You can have any number we want in the denominator except 0. So to get this to equal 0, we would need, either of these quantities here to equal 0. So 2 or negative 1. Why? Right, notice I'm jumping back and forth between the factored version and the not factored version because each piece is important. So the factored version helps us find vertical asymptotes and zeros. The not factored version is going to help us find the end behavior and the y-intercepts. So y-intercepts happen when we plug in 0 for x. So left with negative 2 over negative 20. So our y-intercept is at 1/10. State the domain, sketch the graph. I'm going to wait to state the domain. Let's go ahead and graph this. I'm going to start with my vertical asymptotes. 2, 3, 4, 5. It's a rough sketch, so it does not have to be perfect. My horizontal asymptote is at 1. That was too crooked for me. Perfect. On to graphing. Let's plot our zeros. 2, negative 1. Y-intercept, 1/10. Close enough. All right, as long as you have it labeled somewhere in your work, that's fine. Up next, what we have to do is we have to figure out, well, where is the function going to go? This portion in the middle is a lot easier to see because it's locked in its box. So we can definitely see a downward trend, and we know we're going to follow our vertical asymptote but never ever touch. So something like this, right? Got upside down, decreasing, decreasing. What gets difficult is when we're looking over here. The function does in fact exist over here and over here, even though we're not crossing the x-axis. So we need to figure out where the function is going to be. And to do that, I like to think about what the signs are going to be. So if I were to plug in a number bigger than 4, let's say 6. Is that going to be greater than 1 or less than 1 is the question. So I go and I plug in 6. 6 minus 2 times 6 plus 1 over 6 plus 5, 6 minus 4. We end up with 6 minus 2, 4. 6 plus 1, 7. 6 plus 5, 11. 6 minus 4, 2. 4 times 7 is 28. 11 times 2 is 22. This is bigger than 1. Since it's bigger than 1, my graph's going to go right here. All right, we also know that because we don't have a 0 over here, and we know we're going to hug that horizontal and that vertical asymptote. Let's say we go and we plug in a number that's smaller than -5. We plug in -6. Well, we're going to see a similar thing happen. We're going to be greater than 1. And there's our graph.